welcome back. This is tutorial 11, the one before the last one. And today we're talking about simple linear regression, the first tutorial. For people going to study ECON1310 Introductory Econometrics, we talk a lot about linear regression in there, and the equation you're going to see here. And based on the list of students that we have, probably most of you have to do this other course. So this last week, it's a very interesting topic, very useful for your next course too. Okay. Before that, one very important thing. Well, Happy New Year. This is like the new Chinese year, and it's the year of the rabbit. So Happy New Year. After that, this week we also have Australian Day in Australia. So on Thursdays is a holiday here. What we decided to do was to move our tutorials from Thursday to Wednesday. You might have seen some information at the beginning of the semester. The plan was to move it to Friday, from Thursday to Friday, but some time ago we changed our mind and we're moving to Wednesday. So the next and last tutorial that I'm giving is going to be tomorrow. The same for Peter and Ben. As I have also a consultation tomorrow, we had to move it to 1 hour earlier. So at 3 p.m. tomorrow, it will be my consultation until 4. And at 4 p.m., we start our last tutorial, which will be linear regression 2. Okay? This is about the week that we have in the Australian Day public holiday. Then CML 5 and 6. 5 is open. And we'll close the second attempt for CML 5 will close on Friday. So as usual, as I always say, give it a go. Try to do, even if you did well in the first attempt, it's a good idea to try again. Most people try and the second attempt can tend to increase their grades. So it's a good idea. Another thing, CML 6 is also open and will be open until next Monday. CML 6 has only one attempt. There's no second attempt for it. But the good thing about CML 6 is if it's above any of your CML's best scores, so like the best score of the CML 1 or 2 or 3 or 4 or 5, CML 6 will replace it. So we only consider your best 5 CMLs, and your lowest score will be removed. So make sure you also try CML 6 and try to pump up your grades. It's always a good idea. Tomorrow, I'll talk more about your last LBRT, which is LBRT 3. I'll save it for tomorrow. Otherwise, we're doing too much admin for today. Okay. Next thing, also very good news. These are the results for the whole, everybody from all tutorials, the whole cohort for LBRT 2. Our tutorial did, once again, did a little bit better than average, which is really good. Very proud of you guys. So our mean is almost 2 points above the mean of the general from everyone. And our median is 4 points above the mean. As you can see, we're a little bit more present in this upper part and not so present in the lower part. And if you haven't had enough motives to attend the tutorials, students who attended at least 7 tutorials by now, it would be until last week, so 7 out of 10 or more, had a mean also 2 points above our cohort mean, and the median 1 point up. So as you can see here, even more concentrated to the higher grades. This is only involved, there were 20 students who attended 7 or more tutorials, and this is only considered my tutorial, so not the other tutorials. Okay, so good job. You did really well. Congratulations. Let's keep the bar up, right? Let me open the chat here to see if we have any question. Nothing. Feel free to open your mic if you want to ask something or share something. But I'll start the tutorial. But don't mind if you want to interrupt me, okay? Today we're talking about simple linear regression. At the end of this tutorial, you should be able to formulate a simple linear regression model and interpret the coefficients. We'll be talking a lot about it. Second, estimate a single linear regression equation using Excel. In fact, during the tutorial, we will be receiving the Excel output. So during this tutorial, we're not opening Excel and extracting an ANOVA table. We're just using the output that we receive. Same here, interpret the coefficient of determination and standard error of the regression given the Excel output. So we receive the Excel output and construct a confidence interval for the slope coefficient. Okay, let's go first to the first exercise. First, it is commonly believed by economists that there is a close relationship between annual consumer durables expenditure, so the amount of money they spend in consumer durables, and annual net income. So income is what they receive, right? So the first one, expenditure in hundreds of dollars and income in thousands of dollars. So first, which of the ACDE and ANI would be the dependent variable in a regression analysis? Can I have you guys put on chat which of these two you think would be the dependent variable? And which of these two, then the other one would be the independent. So do you think that expenditure or the money that people spend depends on income? Or is it the other way around? Does income, the money that they receive, depend on expenditure? Please put on chat. You just need to put either ACGE or ANI, or you can put either expenditure or income. It's up to you. Anyone want to give it a go? So let me go to the next one. It makes more sense to say that the amount you receive, your income, explains how much you spend than the other way around. So like if people earn more, they tend to spend more. Makes more sense to say that than to say, oh, when people spend more, they are able to earn more. It's like if you use find some causation, probably the earning more makes you spend more than the other way around, or at least it gives you the earning more gives you the option of spending more, but spending more not necessarily gives you the option of earning more. So having expenditure as the dependent variable makes more sense. So consumer durables expenditure is the dependent variable. Independent variable would be the annual net income. All right, let's keep going. So the following output was obtained with ANI, ranging from $8,000 to $40,000. So this was calculated using values of income from 8,000 to 40,000. So let's start. How large a sample was used? How large is the sample? How large is N? Do you guys want to give me put on chat how large you think it is? I added this advice here, so you could find what the value is. Can someone give it a go in the chat? So here, I know it's the first time we're doing it, so it's a little bit more complicated to interpret the ANOVA table. But by the end of this tutorial, you'll see it's pretty clear. It will get a lot more clear. And by the second one, you'll be used to this one. And can be calculated based on these numbers we have here. Remember the degrees of freedom that we use. Degrees of freedom is usually our n, the size of our sample, subtracted of 1 or 2, depending on the problem, right? But it's the same thing here in the ANOVA table. DF, degrees of freedom. So the residual, degrees of freedom of the residual, it's usually n minus 2. So if you have a look here, since we have an 8, and this is n minus 2, therefore n would be 10. Same for degrees of freedom total would be n minus 1. All right? So n equals to 10. Then state the estimated simple linear regression equation. So this simple linear regression equation is like that. It's a y equals y1, the dependent variable, equals to b0. b0 is the intercept, plus b1, which is our slope coefficient, and xi, which is our observation. It's our independent variable, the value that we observe, so we can calculate y. Let's click. This is the equation, and look where the values of b0 and b1 come from. So y hat, a value predicted, and this little hat here means that it's being predicted. It's the value we're estimating, okay? So the value predicted is equals to 14.783 plus, coming from here, intercept, plus 2.217 times x. So 2.217 is our slope coefficient, times xi. Let me click. How do we interpret that? So with our equation, we would say when income, ANI income, annual net income, increases by 1,000. So the values we have here are in thousands. So when people earn one extra $1,000, you're expected ACD, so the annual consumer durables expenditure, increases by 2.217, which is here, times 100, which is the unit we're using that. So if I put it a different way, when people earn an extra $1,000, they tend to spend an extra $221 in durable goods. Okay, I hope that makes sense. That's the interpretation for the slope coefficient. How about our intercept? What would be the interpretation for it? So to interpret the intercept, let's imagine xi is 0. So if xi is 0, this part here disappears. So this would be the intercept. When ANI, annual net income, is 0, so this guy here is 0. The ACD, the expenditure of y hat, is expected to be 14.783 times 100, which is equals to $1,478. This is interesting here, and think about it. When people have no income, they are expected to spend $1,400. You might be thinking, all right, that sounds weird. Maybe they're getting in debt, borrowing some money. But that is the danger when we try this. What is happening here? We're doing extrapolation of the data. So what's going on here? These data and these coefficients were calculated considering people with incomes between $8,000 and $40,000. $8,000, right? When we try to calculate something, so this would be, let's say, for example, from 8,000, let me see if let me annotate. So from, oh, computer froze a little bit. So from 8,000 to 40,000. When you try to continue this dot line until it intercepts the zero, until x is zero, we're doing an extrapolation. So we're going out of the graph. The same could be done if you go too high. So you're going out of the graph to the right. All right. So using very large x's values or very low x values, in this case, 0 for x, which is to the left of these guys, would be an extrapolation. And it's a dangerous thing to try to make conclusions based on extrapolating the data. Okay, so this value, the intercept, is when you get the x here, move it until it gets to x equals to 0. This value is the intercept, is where the regression line intercepts the y-axis. Slope coefficient, this is a positive number in this case. It's basically this thing here. For every one x to the right, how much y is going up? But in this case, the 1x is $1,000 and the 1y is $100. All right, this is how it works here. Next, interpret the slope. I think that's what we've just done, and the constant value is the intercept. Done. Next, calculate and interpret the coefficient of determination. Here I just moved the answer, so this is not the answer for this one. Coefficient of determination is this r squared, and it explains how much of y, and in our case, y is the expenditure, right? How much of the expenditure is explained by income. So depending on how much people have an income and receive, how much money they receive, how much do they spend, right? R squared is going to tell us, well, the amount that they receive explained from 0 until 1. So if it was a perfect linear relationship, it would be a 1 for R squared. And the other way, if it's like a terrible way, it explains nothing, there's no relationship, will probably be a 0. But here is how we calculate it. Well, first of all, let's go through it together. First, one of the ways of calculating is to look at our sum of squares. So the sum of squares of our regression is 3,618. Have a look at where it is in our ANOVA table. SS 3,618.783. And the total sum of the squares, 4,352. So you just plug in the formula, and it's important to have a good idea where in the ANOVA table each of these values are. You plug in the formula, and we get a 0.8315, which is pretty good. It's much closer than 1 than to 0. So income is relatively good. Well, I think it will ask us to interpret. So 83.15% of the variability in expenditure, so ACDE, our letter Y, can be explained by the regression equation with A and I, the regression equation that we just found here with our X. Okay, so 83%. It's pretty good. It's close to 100%. That was C. Let me check some question in the chat. Not yet. Let's go D. Assuming no assumptions have been violated, predict the ACDE when income. So the expenditure when income is 15,000 and 50,000. What reservations might you have? about these predictions. So let's go. I want you guys to put the value in the chat. So now we're considering, let me see, I hope I know. Have the values. I thought it would be one more slide. Can you please do the equation for this one and put on the chat? What I want you to do is to replace the xi by 15 or 15,000. And I want you to think about a little bit. What value should you have here so you can calculate our expected value of expenditure? Can I have it on chat? It's pretty simple. You just use the calculator. Let me also start doing it together. Where's my calculator? There it is. So 14.783 plus, because our relationship is positive, so it's a plus here, right? The value is positive. 2.217 times. Do I put it 1,500 here? Would you guys be able to say yes or no in the chat? Is it 15,000? Yes or no? Think about it. So remember, our annual net income value is in thousands already. So if someone's saying it's 15,000, the income we're considering, it means we're just adding 15 in here. So 2.217 times 15 equals 48.038. Is that our answer? Or not yet? Think about it. So once again, annual consumer durables expenditure is in hundreds. So we have to multiply this and here, same way that we divided the 15,000 by 1,000, now we need to multiply this guy by 100. So 4,803. Let me click once again. There you go. 4,803.80. Yeah, pretty simple. Just replace the values. Now, 50,000. Look how it looks like. Same thing, 50. So we divided this guy by 1,000 because this is what we're doing here. And it's missing E in there. So 125 times 100 to go back. So 12,000 would be the expenditure for people earning 50,000. But think about something. Remember about interpolation and extrapolation. Look at the range that we're using here for our values. $8,000 to $40,000. So our 15,000 was all right, because it's still inside between 8,000 and 40. But 50, it's a little bit further. So people earning 50,000 is outside of our the amount of observations we have for the X value. And look, sometimes you can't just continue a straight line until the end, because you might be looking at for example, try to think, like, how many cars does someone need? For example, it's not because you're Jeff Bezos or Elon Musk that you need to buy so many liters of milk or so many bread because you're so rich. There is some limit to this linear relationship, right? They can't eat as much money as they have, I think. So look, this is a little bit of extrapolation to why 15 was all right. 50 was a little bit above the limit that we were using. So something to always keep in mind when we're doing a linear regression. Okay. Let's continue. Predictions for A and I, 50 is an extrapolation, which assumes the same linear relationship holds beyond slope of sample. This might not be true. Finally, E. Calculate the 95% confidence interval for beta 1. And in simple linear regression, the little b, this little guy here, is what we calculated using our sample. And then we find a confidence interval for beta 1, which is the slope coefficient for our population. So once again, sample and population, we wouldn't know a specific amount for beta 1 unless you do a census. So what we do, we use the B1 and create an confidence interval. Okay, that's one of the differences. Another difference to think about, in this case, now we're doing simple linear regression. We are using n to -2 for our degrees of freedom in the T table. And because it, as a confidence interval, has plus and minus both sides, so it will be alpha divided by 2. Then, therefore, 95% has an alpha of 5. Dividing it by 2 will be 2.5%, or 0.025. I put the formula in here. This is multiplying our SB1, so the standard deviation for B1. And let's continue. First, can I have on chat the value of this T? Can you guys please help me? Our degrees of freedom, remember, it was n-2, so we found that n was 10, therefore n-2 is 8. And the T is 0.025. Can you guys please help me to find it in the screen? Amazing. Thank you, Minjen. Very good job. All right, so let me click. Exactly. So 8 degrees of freedom and T 0.25. We land in 2.306. Let's continue. So we have 2.306 here. And our S, look, S of B1, it's given here. This is the standard error for our B1, okay? This is the SB1. So in the line that we have B1, B1 is here, and where is B1? B1 is here. The same line, we have a standard error, and that's the one we're going to use. So the slope of the regression lines, just calculating here, adding or subtracting, adding for the upper limit and subtracting for the lower limit, we get B1, beta 1, sorry. So 1.403 is smaller than beta 1, smaller than 3.031. With 95% confidence, we can say beta 1 is between these two values. All right, let's see. Any question for the first one? I understand there's a lot of new things going on there. I hope you guys had a chance to watch the lectures and practice a little bit, maybe. But we will be going today and tomorrow through those exercises in the tutorial, so you get a little bit more used to the linear regression. Feel free to open your mic if you have any question, or to send a message in the chat. You don't have any message up to now, so I will keep going. All right, 2. This time I have something for you. A little poll. It's this poll, although it might look like what we usually do, this time I'm just asking about the units that we're going to use. So let's launch it, just 4 questions. And let's go. A linear regression model has been proposed for predicting electricity consumption in kilowatts based on outdoor temperature in Fahrenheit in northern USA. The monthly consumption data collected to develop the model ranged from 39 to 138 kilowatts. So our X is between 39 and 138. And the outdoor, oh no, sorry, on the other way, I said the wrong thing. Our Y, 39 to 138. And the outdoor temperature data ranged from 25 to 78 Fahrenheit. Fahrenheit is the temperature that we use in the people use in the US and a few more places, maybe, perhaps, probably mostly the US. And there is a little formula to transform to Celsius, if you would like, but it's irrelevant for our exercise, okay? So, what unit would you give to electricity consumption? What unit would you give? Let me have a look at how the poll is going. I have three answers. I still, there's a chance for 10 more people. I now have 5. I'll give you another 30 seconds. Let's think about it. Which units do we measure electricity consumption and why? Which unit do we measure outdoor temperature, which would be our X? Which unit would you give to B0, our intercept? And which unit would give to B1, our slope coefficient, the one you have here multiplying temperature? So I have 6 answers up to now. And 8, 3, 2, 1, go. All right, good job. I'll share the results. And this is the answer here. Look at our equation. Look where the things are coming from. I'll cover a little bit here with the answer. And this is the linear regression. So if electricity consumption is our Y, it's saying it's in kilowatts. So 2 of you got it right. It's kilowatts. This would be the answer, everyone. So the consumption of electricity consumption. Our X is in Fahrenheit. It's an outdoor temperature. Let's see, 4 out of 8 of you got it right. Good job. So basically the temperature. Now it's this the interesting part of interpreting an ANOVA table. The beta 0 is the same unit as Y, because we're trying to calculate the electricity consumption, right? And beta 0 is just the value that it receives when X is equals to 0. So forget this part here. These guys, the value we're giving to our estimate of electricity consumption. So it has to be in the same unit, because there's no transformation we can do for beta 0. Yeah, it's not multiplying by anything. It's just what we say, it's a constant. It's always there. So it has to be the same. So, how many people got it right? 3 out of 8. Good job. It was the most, sorry, let me see. No, actually, I was looking at the wrong one. It was 0. Nobody got this one right. Was a challenging one. Let me see. For the next one, beta 1. Now it's the slope coefficient. And the slope coefficient, it's the one multiplying our X. So our independent variable, let's put it that way. So we're getting information in Fahrenheit, but we want this information to end up being kilowatts, which is our Y, right? So how do I fix this, these units? I will fix it by using a fraction where I get this information in Fahrenheit. So I will divide by Fahrenheit and multiply by kilowatts. So in the end, the Fahrenheits will eliminate each other, and I'll be left with kilowatts, right? So 1 out of 8 answers got this one right. I think this one in units was considerably more challenging than usual. So that's all right. We can keep going. So this is how we think about the simple linear regression. And this always works. beta 0 uses the same units because it's just a constant. And beta 1 is the units from y divided by the units of x. All right? This is how we transform something coming in a different unit into the unit we want. Let's go. Now, state the estimated regression equation. Basically, state this guy here, but let's improve it and use the values we have here. How can we do that? Let's go. I'll click. Look at that. Like we did in the other one, it's pretty much yi. So the estimated value of y, we make this calculation to get the electricity consumption. We get the constant, the intercept. You will notice there's usually more than one name for the same thing, so something to get used to. But in the ANOVA table, usually comes as an intercept. So 169.45. And our slope coefficient, this time it's negative, something that we have to pay attention. It's a plus in here, but the value we have is a negative. That's why in the equation, we can put straight negative. You could also put a plus and then the minus in brackets, minus 1.86, but just to simplify, we just put a minus. So minus 186 times xi, which is temperature. It's our independent variable. So this is the equation. Regression equation, interpret the meaning of the slope coefficient. Slope coefficient is our minus 1.86. As you can see, it's a negative relationship. So look at that. The consumption of electricity Y falls by 1.86 for each increase in outdoor temperature of 1 Fahrenheit. 1.86 kilowatts for each increase in outdoor temperature of 1 Fahrenheit. So this guy will go down 1.86 if this guy goes up by 1 Fahrenheit. Does that make sense? So the higher the temperature in this equation, the lower the electricity consumption. And then you can start relating it to, probably it's talking about heaters, especially talking about the northern USA. It's a pretty cold place there, it's close to Canada. And if you think about heater using a lot of electricity for your heater, when it's colder, you're probably using more when it's colder than when it's warmer. So when it's getting warmer, we're using less electricity. Now, let's try to do a prediction as we did before. Predict electricity consumption when temperature is 50 Fahrenheit and when it's 90 Fahrenheit, and comment. Can we start in the chat by trying to predict how much would be our electricity consumption if our X is 50 Fahrenheit? Can you guys please put it in the chat? It's pretty simple calculation here. Pay attention how the equation is. You just replace and plug it into your calculator. Let me start doing it now with you. But if you finish, please put it on the chat. Quite simply following the equation. 169.45 minus 1.86 times 50. This time, there's no transformation, 100,000s. We're talking one by one. Equals 76.45, probably kilowatts, right? Which is our unit. Let me close this one. 76.45 kilowatts. Simple, easy. So let's do the next one, 90 Fahrenheit. Can I please have your answer in the chat? Same process, same everything, but instead of 50, it will be 90. Do you think you guys can solve it in the chat? Let's start doing it. So 169.45 minus 1.86 times 90 equals minus 150.95. Did I do anything wrong? I did. 169.45 minus 1.86 times 90. That makes more sense. 2.05. There you go, 2.05. But there's something going on here. Once again, look, the range of the observations we used to calculate this linear relationship was between 25 Fahrenheit and 78 degrees Fahrenheit. So 50 is all right, but 90, it's above the maximum 78 Fahrenheit. So we are once again talking about extrapolation. We're trying to use a linear relationship that works for a small space and try to use it for outside of the sample, values outside of the sample. So let me click a little bit. So this one is okay, it's within, but this other one is an extrapolation and the result might be biased. And there's some logic to think here. As the temperature goes up, while we will be using less heater, there's a chance after a certain temperature, we'll start using air conditioning. So although there is this negative linear relationship going on with our temperature and electricity consumption, after a certain point, maybe it goes the other way. So it makes a little bit of a curve or a kink, or maybe it becomes flat. But yeah, we start using aircon when it's very warm. So the sample linear relationship will not hold past 78 Fahrenheit, because when temperature increases, more electricity use is expected due to fans and air conditioning being used. The problem with extrapolation. All right. So that's the issue here for D. Anything in the chat? Nothing yet. Now let's look at our coefficient of determination again. So our R squared. We have our sum of squares. Can you guys get the answer in the chat, please? SSR divided by SST. SST is the total sum of squares. SSR is the regression sum of squares. Pretty much it's here. You have one value in here and one value in here. Divide one by the other, and then you know how much of the variance in Y we're explaining with our regression. Let's keep going. So this value on the top here, then the one in the bottom, and we're explaining 0.8939, which means 89.39% of total variation in electricity consumption, Y, is explained by the relationship with temperature, X. All right. No questions in the chat, so we keep going. Look at this new guy. Compute the correlation coefficient. You remember what correlation is? You probably heard about it before. Correlation is when it could be from -1 until 1. So there is a negative correlation for something. So when something goes up, the other one goes down. It's a negative correlation. And a positive correlation, which would be when something goes up, the other one goes up too, or the one when one goes down, the other one goes down. If there's no correlation, It's like one changes, the other one doesn't change. That's a little bit how it works. And it's nothing different than our R square, our coefficient of determination. The only thing is that we need to be careful because R squared is always a positive number. So it doesn't carry if the relationship is positive or negative, if the correlation is positive or negative. So you need to be aware of our B1 there. All right. So for our R, you just take the square root of R squared that we just found, 0.8939. But because B1 is negative, you need to add this little negative there. And our correlation is 0.9455. Okay. That's it. That's the correlation. It's a negative correlation. It's almost linearly correlated, like almost 1-to-1, but it is it's negative. Yeah, there is a high negative correlation between electricity consumption and outdoor temperature, at least for our sample. Next one, determine the standard error of the estimate. And this is different than the one that we've just done before. Before, we look at the standard error of our B1. So B1 is here. There's a standard error for it. There's also B0, a standard error for it. But now we want the standard error of our estimate. And look how it's calculated. Okay, so let's go. The standard error for our estimate is like standard error of estimate divided by degrees of freedom. Degrees of freedom, remember, the residual is 22. Oh, sorry, it's already there. N minus 2, our N would be 24, but N minus 2 is there, so 22. And our sum of squares of the estimate is this residual here, the one that is left. So you divide, take the square root, and we get an 11.63 for our standard error of estimate. So S little e is different from S little b1. Okay, that's important because that's very confusing sometimes. This is the standard deviation of all points around the estimated regression line. Okay, so when we look, let me go back a little bit to the extrapolation graph. This is how much the numbers are oscillating around our estimation line. It's a simple linear regression, so we're trying to calculate a straight line, but the values of y that we observe, they might be a little bit above and a little bit below. So this standard deviation shows how much they're oscillating. If the value is really high, it means they're all around. So you will see the scatter plot here points all around. Or if it's pretty much linear, our standard deviation of the estimate would be relatively small. Okay, that's it for this one. And this is the end of exercise 2. Do you guys, we have quite plenty of time. Do you guys have any answer? Do you want to put something on the chat or open your mic? No? So I'll keep going for our last exercise. Once again, we'll have a poll. And now, not too difficult, but I'm asking you to put everything in our linear equation. Oh, did I? Let me launch the poll. There you go. It's not super challenging, but try to pay attention to what we're doing here. So a large corporation was interested in determining the relationship between the value of its loan portfolio, billions of dollars, and its level of profits. millions of dollars. Using quarterly data from its previous 6 years, it estimated the following. Y is equals minus 16.3 plus 32.7 times X. And then they give us an error sum of squares, 937.43, and a sum of squares of X, 287.21. Then finally, they ask, determine a 99% confidence interval for the slope coefficient. In this case, the slope, well, first, let's focus on our poll. I have one answer out of 13. I'll give you guys another minute. So let's think about the value of the loan portfolio. Is it a Y? Is it a beta 0? A B0? Is it a B1? Or is it X or SSE, SSX, or N? I gave you a lot of options, but there are, you can, if you want to do it a little bit, the easiest ones, you will see the values in the equation already. So for minus 16.3 and for 32.7, it's pretty clear what they are about, which one are you using for the standard simple linear regression. So it will be pretty easy to find which values to give to these two. These other two can be a little bit more confusing. So think about, Y is the dependent variable, X is the independent variable. Does it make sense? What makes most sense? For the value of its loan portfolio to explain profits, or for profits to explain the value of the loan portfolio? Think about it. And I have 6 answers now. I'm about to close. Any last people among the 13 that we have in chat in a tutorial? 7. Okay, another 3 seconds. All right, 7 answers. Let's go. I'll share the results and let's have a look here. So it makes more sense for our profits to be explained by the size of our portfolio than the other way around. So we have a portfolio of a lot of money, and that's how much it profits. So if it was very small, it wouldn't make sense to have very large profits. So that's why it makes more sense to have profits being explained by the size of the portfolio. So size of the portfolio is the X, the independent variable, and profits is the Y, the dependent variable. Then, as you have here, minus 16.3 is our B0, and 32.7 is our B1. Let me put the numbers on it. So first one, we got just 1 out of 7 got right for the one. For the second one, just 1 out of 7 got right the second question. The third one, a B0, 1 out of 7, and the last one, B1, 3 out of 7 got this last one right. So good job, whoever got it right. And if you didn't, it's natural. It's the first time we're dealing with simple linear regression. So don't worry too much. It's important to get used to this little equation there. All right, look at that. So this is the information we already have. I've put a few very important slides that might be very useful for your CML6, because this is all about, not all of them, but like most of the useful formulas you have, especially the ones dealing with sum of squares. And this one's talking about confidence interval for beta 1, right? So let's go. Determine 99% confidence interval for the slope coefficient. There was one more variable tucked in between our question here. It's hidden, but it's good for you to see for the first time now, so you start paying attention to in other questions. Look at that. Using quarterly data from its previous 6 years. So quarterly data comes from a quarter. Each year has 4 quarters. So N was there in the question too, although it wasn't very clear. but we're looking at 24 observations of our sample. That's our sample. All right. Now, let's go. Let's use the formula that we have for that slide. Once again, alpha, it's a confidence interval, so there's upper and lower. So alpha is divided by 2. It's a two-tailed test, right? Alpha divided by 2 and minus 2. So we used to have a 24 and minus 2 will be a 22. But then we need SB1. So the standard error of B1. Thing is, it's not given. We don't have the ANOVA table to just extract this number from it. But we can calculate using this little formula here. SB1 is equals to the SE, so the standard error of the estimate, divided by the sum of squares of X, SS, XX, or SSX. Sometimes it's just 1X, sometimes it's 2. It's the same thing, okay? This we have, so just 1X here, 2X there. This we have, and I was going to say, so we can, so this little guy we have, but SE we also don't have. So we need to resource to this other one. If we had the ANOVA table, we would know, but we don't. So can I please have it in the chat, this value here? It's a simple calculation. Now you have everything to calculate the standard deviations of the estimate. We have SSE and we have N. So can you guys calculate this one here and put on the chat, in the chat? The square root of this fraction. And let's go. So I'll start by the division. SSE is 937.43 divided by, we had N, which was 24. See, I open a little bracket there. But we need to subtract 2 for our degrees of freedom. So it will be 22, 24 minus 2. This division is equals to 42.610454554545. And then we need to take the square root of everything. So I'll click this guy, square root, 6.527668385. Okay, important because we're carrying all these values to use a lot of decimals. So it's more precise. There we go, few decimals there. Now we can replace it here. SSXX we have to calculate SE. So we have SE, put it there. So this value we calculated divided by SSXX 287.21. But we don't want it this way. We want the square root of it. So square root, it did it for us, square root of the thing, equals 0.3815175. 0.3855175, and the rest. Finally, we just plug it back. And we have this one. And as a last one for this tutorial, let's have a look at the t-table to see what we're using. We were talking about a 99%. So I actually did a mistake here. This is not 0.05. It will be 0.005. You guys, I will apologize. So we can have the correct value there. Will be an extra 5 in here. I hope the next one is correct. Yeah, 0.005 for the next one. So let's come back to our reading view. Can you guys give me a hand? So 0.005 and 22 degrees of freedom. Can I please have on chat? Oh, I think I'm covering, right? 0.005 and 22 degrees of freedom. Do you guys think you can find it in a table? You've been extra quiet today. I know that I think the content is a little bit more challenging, but the t-tables they still working pretty much the same. So for the t, 0.005 in here and 22 degrees of freedom, we find 2.819. So let's replace it back in our equation. So 2.819 times that value, and this is our confidence interval, and we find beta 1 is in between 31.614 and 33.785. And that's our 99% confidence interval for the slope coefficient of the population. This is population. This was sample. This is population. All right. Let's see if there's anything written. No. So today, during the tutorial, it was the simple linear regression 1. What we did today, at the end of this tutorial, you should be able to formulate a simple linear regression model and interpret it, the coefficients. So our equation y equals to b0 plus b1 times x. That's simple. And interpret what b0 and b1 are and y and x. Then estimate a simple linear regression equation using Excel. We didn't do it. We got our results already in the tutorial. Probably this one is not updated. Interpret the coefficient of determination and standard error of the regression given the Excel output, and construct a confidence interval for the slope coefficient. All right. So thank you so much for joining today. This is the one before the last tutorial, and I see you tomorrow in the next tutorial. Have a good one.